Okay, y'all, so I will be getting the exams back to you on Thursday. The written part is graded. I'm still making my way through the coding questions. So I'm looking both at questions that received a perfect score and at questions that where there was a 0 and awarding partial credit. The reason I'm looking at the exams or the code that had perfect scores is we asked you to do certain things, such as to pass all your objects by reference. And if, for example, you don't pass your objects by reference, there's a deduction. And in looking through the exam, I'd say 75% of you are still not passing objects by reference unless you're modifying them. You have to get into the habit of passing all objects by reference, regardless of whether or not you modify them. Okay, again, the reason is efficiency. If you pass a vector by value and it has 1,000 elements, then the compiler has to generate code to copy 1,000 objects to your function. And that's a waste of time, okay? Instead, pass it by reference so that it accesses the object in the calling function and you won't have to copy all 1,000 elements of the vector. Even strings in general should be passed by reference, not by value. So that's an example of a deduction that I'm making on the exam. So I'm mentioning it today because you have a lab due this evening, and I think actually there Dr. Plank specified what the parameters should be, but you really need to be in this habit of passing objects by reference regardless of whether or not you modify them. Okay. Now today I'm going to go over parts of Lab 7, which is the Coke processor lab, because I'm seeing some issues on Piazza with the understanding of what to do in the cases where you delete a user and in the case where you're deleting a code processor object. And I think the confusion from what I'm seeing leads back to a misunderstanding about the data structures involved. So I want to go over that, and then we're going to go and finish linked data structures. Specifically, we're going to be going over linked lists today, and in Lab 8, which you'll be starting tomorrow, you'll be implementing linked list. Okay, so with the code processor lab, there is, well, let me bring it up first. There's kind of 4 major data structures which you can see down here at the bottom. So you have a map with names, and that map is essentially, so it might be, for example, I'm going to create a conceptual view of it, not the way it's actually implemented. So I'm going to show it as though it's a vector, but in fact, remember, it's implemented using this tree-like structure that we'll be getting to in a few weeks. But for example, it might have BVZ and say Chuck and Mary. So this is the names. In fact, I'm not going to have enough room here, so I'm going to come over and do it on this one. So might have names, and we'll have BVZ, Chuck, Mary, some other ones. And each of them has a pointer to a user object. Okay, so the key is a string, and then each of them have a pointer to a user object, which has information about that particular user. Then, the next, and so that's the names data structure. The next one is phones. So that is you can see the key is a string. That's the name of the user, and then a pointer to the user record that is associated with that particular user. So we'll just put that down for a moment, and then we'll talk about it. So we also have, this is names, and this is phones. And the strings here are telephone numbers, like, say, 207-1580, say, 486-3153, 980-1211. I know they'd probably have area codes. And then they point to the user that has them. So, for example, maybe I registered 2 phone numbers with Coke, okay, and then maybe Mary registered 1 phone number. And what this data structure gives us the ability to do, if you're thinking about Coke and you're implementing this rewards program for Coke, and you're allowing people to text you with Coke codes, when a code comes in on a text message, your identifier is not the person's name. Your identifier is the phone number. And you then have to be able to use that phone number to find the user and credit their account with some reward points. So that's the point of having the phones data structure, is so that when we receive a text message from the user, we can map that phone number to a user. And when the user registers a Coke code, or I'm sorry, registers a phone, they do it using add phone, and you see they give you the username and the phone number. And so you can use, when you do add phone, you can use the username to find the record, the user record. So let's say that I had add phone, BVZ, and it's 921-4000. So then I can use the names map to find BVZ. So there's BVZ. So I use the names map to get my pointer to the user record for BVZ, and then using that, I can enter the new string here, 4000, and now I have a pointer to that user record that I got from the names map, and I'm able to make this entry in phones point to user. Now the important thing to note here is that users are pointed to by 2 different data structures. You have the names data structure, which can point to a user, and you have the phones data structure that can point to a user. Okay? So there's a, then, come on, there we go. So the first confusion has come up with what to do with delete user when we delete a username. Okay, so some person chooses to remove themselves from the rewards program. You can see here that delete user is going to have to remove, let's say we're removing BVZ. I choose to remove myself from the Coke Rewards program. Okay, so we're doing delete user. Okay, so what's one task that I'm going to have to perform here? If I want to delete BVZ, what's one task that I need to perform? Yes, Sarah?
You need to also remove the phones associated with it.
I need to remove all the phones associated with this user. So I have, you can see I have 3 phone numbers associated with BVZ. Okay? Now, how do I remove the phone number? Let's get back. I'll just say remove phone numbers. So we'll just list the tasks. Remove phone numbers associated with BVZ. What's the second task we have to do? Yes, Ardlin. Okay, go. When you say go through the set in the user class, what? Pardon? Okay, so you're right, but that's how we're going to implement task 1. Okay? So you're kind of saying the same thing Sarah is, which I have to remove phone numbers associated with BVZ.
Yeah, then you figure out what the phone number is and you erase it.
Right. Right, you're right. I guess what I'm saying is it's a second. Just a sec. So that's both you and Sarah are talking about the same thing, which is removing the. See, Sarah's saying you have to remove the phone numbers associated with BVZ, and you're telling me how to do it, which is good. But there's a second task that's kind of. Senior. Okay, right. So second task is we have to delete the user record associated with BVZ. So I'm using ASSOC means associated with BVZ. There's a third task. Yes, Sarah.
You need to remove the username from the names.
I need to remove the username from names. Okay? So those are the 3 tasks I need to perform. Now, there's this order to which these tasks need to be done. Okay? There's one task, of these 3 tasks, one of them has to be done last. Okay, which of the 3 tasks must be done last? Doug?
The second one.
The second one. Yes, very good. So the task that I have labeled 2 must be done last. The reason is this user record contains information that I need to remove the phones. Okay? And in general, we don't want to remove or delete an object until all pointers to it have been deleted. Okay? I've noticed in some of the code that has been published on Piazza that you are deleting objects, and then after you delete them, you're still trying to access information from them. That can result in a seg fault because once you've deleted the object, the memory manager is allowed to give away that memory, is allowed to zero out that memory. So you cannot assume that once an object has been deleted that you may access its contents. And therefore, you need to delete the user record last. Okay, now it doesn't actually matter which order you remove the user from names and phones. That can be done in any order if you're a little bit careful with keeping a pointer to user. But deleting the user record, that needs to be done last. Yes, Alan?
I don't understand why wouldn't it, isn't it both possible and easier to delete the user object and then remove the record from the name tag?
Okay, so let's say okay, just a second. So I haven't told you yet how to remove the phone numbers from the phone's vector.
I'm not talking about step 1, I was talking about the order of step 2 and step 3.
Okay.
I thought it was the right order, the way you wrote it, and then you drew the arrow, and that confused me.
Okay, so the problem is if I delete the user record from BVZ, let's say I call delete user.
Yeah.
I still have a pointer from names to this deleted object. That's a dangling pointer. That's not. So just a second, Alan. Let's say I do it in the order 1, 2, and 3. Okay? I'll ignore the fact. So I first remove the phones. Okay? So the phones, I'll just put an X next to them right now. So right now, X, X, X. So these pointers, I'm just going to remove them. Like that, they're gone. Now I delete the user record, okay? What do you notice about still pointing to something? This is a dangling pointer. Now I understand that technically speaking, we're never going to do anything dangerous with this dangling pointer. But I don't like to do this. I think it's very dangerous to leave a pointer to a deleted object.
But that pointer is the value field of the map entry. Aren't we about to erase that map?
We're about to, okay? You know that. Let's say 6 months later, someone comes into your code who's not familiar with your code, okay? And they're unfamiliar with things, and they try to go after the deletion, after step 2, but before 3, they try to do something like they say names dot find BVZ. Okay, they get it, so they get knit equals, that succeeds. Now they're unfamiliar with your code, so they now say knit second phones, and it core dumps because the user record was already deleted. Okay, so my point is, you know right now as you do it that you're deleting the user record and that you should never access it after that. But the danger here is that in 6 months or a year, someone is going to possibly come in and modify your code. And they're not going to realize the danger that was there, which is that you temporarily had a dangling pointer. So I'm very reluctant to ever leave a dangling pointer in my code. That's why I'm so kind of insistent that you delete the user last after all pointers have been removed.
Now you're still going to have a dangling, I think what you're saying is you're still going to have a dangling pointer, whichever temporary pointer.
True, but
it looks less
yes,
tempting to use.
it looks less tempting to use, exactly.
I get it.
Exactly. Okay, so that's why I'm making such a big deal of it. I guess, yes, I'm a bit of a neat freak, okay? But I think in the long run it's safe. But you're absolutely right. There is a dangling pointer lying there somewhere. It's in a temporary variable, though, so. Okay, yes.
What's the difference between delete and erase?
Okay, so question is, what's the difference between delete and erase? Okay, so delete is an operator that is, let me actually say it on this page. So delete is an operator implemented by the C++ language itself. That returns memory to the heap. And executes an object's destructor. Okay. Erase is a method implemented by different STL objects, or in this case, your own class. So in this case, is a method implemented by a map object and removes an entry from, actually it can be a map or a set in this particular So delete is a built-in operator in the C++ language. Okay? Whereas erase is a method that's implemented by different classes. Okay? So it's true that erase, in some sense, erase may be returning memory to the heap, but it may not. Okay? In this case, it is returning some memory to the heap, but it's certainly not erasing the user object. It's simply removing the string, that key, from the table, from the names table. Okay?
So it's like I call delete and then I'm free to like erase the.
So what I'm saying is you want to call all your erase methods before you call delete. Okay? Because erase is going to be removing references to this object. So this object right here, this is the object I want to delete. Okay? So I'm going to call delete eventually to what's going to happen. So let's actually rearrange this down here so that we have it in the right order. So let's make this 2 and this 3. So eventually this is going to be a delete user record, whereas the first two are going to be implemented by using some kind of erase method. Okay, because in 1 and 2, in 1 we're removing it from a phone set, which will use the erase method, and in 2 we're removing it from the names map, which will use an erase method. Whereas in 3, we're using the delete operator because we're directly deleting a piece of memory. Does that make sense? Are you still a little... Alan, you can...
I just feel like I should say, I told them to do 1, 2, 3. I mean, sorry, the old 1, 2, 3. 1, 3, what is now 1, 3, 2. Because it avoids needing that temporary pointer, and it just, you know, because I didn't see what you were saying now.
Right.
So I think that they may be confused about that.
Okay.
And I want to point out that the difference between doing 1 first is for correctness. You don't do 1 first, it's not going to work. But the order of 2 and 3, I told them the wrong thing, not in terms of correctness, but in terms of readability.
Okay.
And maintainability. And
Okay.
to your way. Just
Okay.
to clarify.
Gotcha. Okay.
No, you got to create a temporary pointer because if you delete
Here, let me show you what Alan's saying. So essentially what we're saying is that you first would do something like, say, let's say I have delete user and it's BVZ. So first what I need to do is create, in effect, a temporary pointer. So let's say I get, we'll call it nit for name iterator. Let's say I say name iterator equals, and I know I'm doing this a little with pseudocode, but I say names.find BVZ. Okay, and obviously you can't hard code BVZ, it has to be. Then you would say something like temp equals, or I'll say temp user, because I like to be a little, is nit second. Okay, so now I have a pointer. So now I have temp user. So what I've done is I have this variable temp user, and I have it temporarily pointing to user, to my BVZ record. Okay? Now, what I do is, third step, is I need to remove, let's say I remove BVZ from names. Okay, if I do that, what happens is it removes this entry and removes this pointer. Okay, but I still have this temp user pointer to user. Okay, now, step 4 is I would like to remove the phone numbers from phones. Okay? So what's an obvious way I could remove, seemingly, phone numbers from phones? Because unfortunately I'm seeing some code that does it this way. The code, the way not to do it is to do a linear search through phones. Okay, I've seen some code where people create a phones iterator and they go through each entry in the phone set, check to see whether the user is BVZ, and if it is, delete it. Okay, just like so. So Coke is a big company. It may have 100 million registered users. To do a linear search through, and they may have, say, registered each 2 phones, so that's 200 million phones. So to do a linear search through phones, looking for BVZ's phones is going to really slow things down. It's hugely inefficient. Okay? That is why each user record, if you look at each user record, each user record keeps a set of that user's phone numbers. Okay, Sarah, I'll get to you. I just need to, I want to get through this, okay? So each user also maintains a set of their phone numbers. So what we have for BVZ, if we were to look at BVZ, what we would see, let's see, this is getting a little, unfortunately, do it like this. So there is, no, it's too small. This is one time where I wish I could write really, really tiny. So there's a phones field, which is a set, and it has, I'll just have to do kind of 207, 486, and 921. So you get an idea that that's just, I'm using the prefixes. In fact, I don't have room for the whole phone number, but the BVZ record has a set of phone numbers listing which phone numbers I registered. So when I want to execute step 4 here, which is to remove phone numbers from phones, there is no reason to do a linear search through phones. Instead, I can go to the phones field of BVZ and simply iterate through that particular set, which has only 3 phone numbers. And for each one, I can find that phone number efficiently because phones is implemented, this phones right here is implemented as a set. So I can get it efficiently, and then I get an iterator to it and I erase it. So essentially what I do here is I say for each phone number, and let's get the right name of it, it's called phone numbers. So for each phone number in user phone numbers, I need to essentially have a phone int which will, from phones, find that phone number, and then I need to call phones dot erase on it. Okay? I answered it. Okay. Camille.
I did step 4, but because that you have to know, like, you have to know the set of phone numbers that is BVZ's phone numbers, then you can't remove the BVZ from the name before you do that, right?
Yes, you can. And the key thing was because I did step 2. So step 2 allowed me to retain, sorry, I'm having trouble getting a cursor. There we go. See, step 2 created this temporary pointer to user. So even though I had removed the entry from names, I still had this temporary pointer to user. Okay. And go ahead, Camille.
So, I know you've probably said this before, but just in like me asking a question, maybe
That's fine.
for like framework. So you can't delete the user and then erase the dangling pointer.
That is not good practice. You could, but what I've seen on Piazza is that, so the reason I'm so against it is I actually saw on Piazza code where people erased the entry from the names field and then they tried to go through the iterator and still get to that entry. And that's why I'm so opposed to it, because they were using the dangling pointer. Okay? So instead, what I'm advocating is to keep this temporary pointer to it. As long as you have that temporary pointer, then you can erase the entry. Okay? And you'll still, erasing the, I think what many of you are confused about is you somehow think that erasing the entry is somehow deleting the user record, and that's not happening. It's only removing a pointer to the user record. Okay? And that's an important distinction. Okay? It's only when you call the delete operator that you actually physically delete that object. Okay? Is that, get it? Okay. Yes.
Well, in
Very good. So this is the problem that Alan was talking about, okay? So you're right. After you are done with step 4, okay, you will have removed these 3 pointers, okay? So step 5, is to delete the user object. Okay? So step 5, I do blow away the user object. And as you say, temp user now is a dangling pointer. I cannot avoid this issue, okay? The very last pointer, so I should only delete an object when there's one pointer left to it, okay? That variable, whichever is the last variable that I point to, when I call delete, I'm going to make a dangling pointer out of that variable, and I can't avoid doing it, okay? My claim, and this is based on kind of what I saw on Piazza, is that at least this is a less tempting target to try to access something through than keeping a pointer through the names map and trying to do it that way. Okay? So no matter what, you are going to have a dangling pointer. It's just, this is, I have found through experience, this is the best way to do it. Okay? It minimizes problems, especially in what we call legacy code, when some other programmer has to come in and modify your code. Okay? Yes, Alan?
Here you still have removed phone numbers associated as number 1. And the next one you have is like number 4. Do you care which order that happens in? So I had told them to do that first while they still had access to the other. Since they're making a temporary pointer, it doesn't matter.
It doesn't matter which order you do it in.
Okay.
I could have just as easily, I know I did it this way, and this is probably not good from a pedagogical standpoint, but in fact, it would have been equally good if I had made this step 3 and this step 4. In this case, the order of those two operations is unimportant. It truly is. So whichever order, if you've done it in 3 and 4, perfect. Okay, is that the order you told him to do it?
Well, I
Or-
told them the very first. Well, I guess.
Okay.
Step 2 because I didn't have.
Okay. Okay. Either what I'm saying is steps 3 and 4, the order is unimportant. Okay. Steps 1 and 2, the order is important. Step 5, the order is important. So 1 must come before 2. 2 must come before 3 and 4, but 3 and 4 can occur in either order, and 5 must occur last. I'm going to say that just, okay. I don't want to get into nuances, okay? So I'm going to say this is the way I want it to look. If you got it to work some other way, don't change your code, okay? It's fine. You got it to work. Don't change it, okay? Yes?
So I understand what you're saying. This is like a professional way, like in general, if you had like more complex things going on, but it's like my delete user is like 8 lines or something. So
Right, but if you get into this habit early of doing things in a kind of, see, you're saying my delete user is small, but I've already seen code on Piazza that was trying to make, that was basically saying knit equals names.find, then names.erase NIT. And then I was seeing NIT second phone numbers. Okay, that's bad. Okay, so even in this 8-line piece of code, I was seeing this problem popping up on Piazza. So that's why I'm making such a big deal of it, because maybe it didn't happen to you, but it was happening to other people. Okay, and it's kind of like trying to squash this bug early, because it's a dangerous habit to be in, is all I'm saying. Okay, and since I'm already seeing it happen on Piazza, I know it's dangerous, even in an 8-line sequence. Still, if you got it to work, don't change your code. Okay, yes?
For the destructor,
Mm-hmm.
it says we don't.
We're going to get to that. This was just delete user. We're going to get to the destructor in a moment. Okay, other questions? Okay, the destructor is a second thing that's confusing everyone. Anyone have other questions for delete user? Have you got this down? Okay, yes.
I'm trying to submit my code when I follow these steps, but like currently the code that's submitted to Labs now is just like I did 14325, and I just used like a bit second phone number.
14325. Okay. If it works, it works. But what I'm saying is this could segfault on certain compilers.
All right.
Okay.
Well, I did fix it. I'm trying to submit
Right.
it.
Well, if it was working, I don't really want you changing it. Okay. It is what it is. Okay. Other questions? Yes, Sarah.
Do you care about like a Piazza post about this? Because I'm better at reading something or something. So if I make a Piazza post with these other people,
Mm-hmm.
need to read it.
Yep. Mm-hmm. That's fine. Okay. Other questions? We good? Okay. Let's move on to the destructor. This is a separate thing. So deleting a user is a user removing themselves from the program. Deleting a code processor is equivalent to Coke saying we're shutting down one of our rewards programs. Okay, we're shutting down so it's maybe Coke has, say, 5 different rewards programs, so it had 5 instances of code processor, and it's shutting one of them down. At this point, what happens is this destructor right here gets called. It's the thing that has the little squiggly in front of it. And when we shut it down, what we're doing is we have to delete all of our users. Okay, so we have here, we have a set of names with all of our users, and we also have a whole set of prizes. Okay, so what we have, going back to here, is first of all we had this big huge setup where we had phones and names, but we also have another data structure which is prizes. Okay, and prizes is a string and then a pointer to a prize. So some of the prizes might be say a blanket, a trip, let's say a phone. So each of them have pointers to something that describes that prize. So when we shut down our code processor, we need to do a number of actions. Okay? The order of what I'm about to do is, again, I'm going to write down which order did you tell him to do it in, Alan, so I don't.
For the destructor,
Do you remember?
I just told him to delete, to go through the either the prize map or the user map, delete all the, call delete on every.
Okay. So it doesn't, I just didn't, you didn't specify a 1 and a 2.
Between prizes and user?
Yeah.
No.
Okay. So I'm free to, I just don't want to get, okay. So one task you need to do is go through prizes and delete, go through the prizes map and delete each prize object.
Do you have to create like 10 values because you aren't actually erasing?
No. In this case, what you can do is you can basically write one of those things where you have for knit equals something begin. Again, I'm not writing it fully out, but something knit begin, knit not equal end, knit plus plus, right? And you have to figure out what goes into the dot begin dot end. So you're iterating through the maps array. Okay? And then you can say delete knit second. And that will delete this object. And then you can say, actually you don't have to do anything else. Okay, you might say, well, why don't I also have to erase the entry from prizes? The answer is, since the whole class is going away, okay, this map is automatically going to get reclaimed when the class goes away. You don't have to actually remove the string from the map. You only have to delete the object that it points to. And you're only, basically, the rule is anything that you created using new, you must delete when you go through the destructor. So a good rule of thumb is if you created something using new, okay, and it still exists, when the destructor gets called, then you must destroy it using delete. Okay, and if you look through all of your code, you'll find there's only 2 places where you call new. You call new to create a prize, and you call new to create a user. Therefore, in the destructor, you only need to ensure that you delete all of your prize objects, and that secondly, you delete all of your users. Okay? You don't have to remove the entries from the map. If you did, fine. Don't worry about it. Just saying it's unnecessary. Okay? So that's step one. Go through the prizes map and delete each prize object. Okay, if you happen to do this second, that's fine. The second thing you need to do is you need to go through names and delete each user. Okay, so here you'll go through names, and there's one object for Chuck and one object for Mary, and again you will delete them. And there was some chatter on Piazza about whether you have to go through both names and phones. And I think last night I got a little confused myself with what question I was answering. I said you had to go through both. You only have to go through names. You don't want to go through phones in this case. Okay, because names has a single pointer to each user object. Now you're thinking, okay, I got rid of these objects and I have all these dangling pointers. That seems like it's bad. Okay, but those maps are getting destroyed anyhow. And therefore, it is unnecessary to remove the entries. If you want it to, that is fine for the time being. Okay, because I know it's very confusing right now. But the only things you have to delete in the destructor are the things you created using new, and that was the prizes and the users. Okay, so these two steps here. Yes.
So it doesn't matter whether we, so for the second step, it doesn't matter whether we go through names and run remove user, or if we just delete the user object and leave names.
Yes.
Names
Mm-hmm.
as they are.
Yes. So some of you might have been clever in the destructor. I would actually consider it is there a delete prize? Actually, there is no way to delete a prize. You could have actually, I'm not advocating you doing this, but you could have rolled through, and I don't even want to say to do it that way. That's, I think that's going to be too complicated. So yeah, just do it this way. Okay. And what I'm saying is if you also went ahead and erased the name from names, it's fine. It's extra work that you didn't have to do, but it's not hurting anything. Okay. So questions about this? Alan, anything to add?
I guess just to make sure I have it straight, we
Mhm.
only need to delete the prize and user objects.
Correct.
Because the maps themselves will be erased
When the class, yes, the delete operator automatically deletes the memory associated with the map and with the prize map and the phone map and the user map.
So we don't. So there is no point where we have to ourselves delete them.
Correct.
Because
Right.
when the program's done, it'll delete them.
That's right. You'll notice that you never had to call new to create any of those three maps, right? They just kind of appeared magically when a code processor object was created. And therefore, they will also disappear magically when the code processor object disappears. Okay. I know this is a lot to take in. Okay. This is, in my opinion, with pointers, probably the hardest part of the course. So it's one of those things where practice will help you get better with it and will help you understand things better. Right now, I'm trying, and Alan and I both are trying to give you, and Casey and her labs are trying to give you more cookbook approaches sometimes to how to do things. But as you do it more and more, we also want you to kind of understand at an intuitive level what's going on, because that will be important as you go on in your careers to being an efficient manager of memory, because memory management is one of the most crucial things or tasks that you perform as a programmer. And having an understanding of how memory is being managed by you and by the system is important, because it affects the efficiency of your programs. And of course, it also affects the correctness of your programs. Okay? So any other questions about this? Very good. Okay. So we may have to finish up what I'm going to start in lab, but at least we will get started today. So we started talking 2 weeks ago about linked data structures. I know it was a long time ago, so quickly review. We were talking last time about implementing a stack. If you remember, a stack had 2 fundamental operations. So you had a push operation which would add a new object to the front of the stack. So here we have 3 operations. We push give, so that puts this object on the stack. Then we push him, and that pushes him onto the top of the stack. Then we push 6, and that pushes 6 onto the top of the stack. And then if we do a series of pops, we always remove the most recently added object from the stack and return it. So if we do a pop, 6 was the most recently added object, and therefore it is what gets removed. Okay, just like if you have a, well, in this case, a set of papers, if I set them down, boom, 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 and I pick it up, okay, this is the top paper that I get is the last one I put down. And we went through a list-like implementation for it. I told you that vectors were a perfect implementation vehicle for a stack, because vector, you add something to the end, remove something from the end. It's very effective and efficient, but we want to show you how linked data structures get implemented. So that is what we did last time, and we went through the process of linking it up. I don't want to repeat doing it for a stack. I want to move on to something new. So we're going to move on and talk this time about queues. Okay, so a queue, conceptually, we'll start with conceptually, is like a queue in a grocery line. So conceptually, you have people that come into the queue, like let's say Brad, Mary, Chuck. But instead of removing the most recent person from the line, you remove the person who was first in the line. Okay, that's what happens at a grocery store. There'd kind of be a riot if, let's say, I got there, and then Scott got there, and then the cashier said, and next we're going to process Scott. And then Camille comes into line, and then Alan, and he says, okay, next we're going to take Alan, and then we're going to take Camille, and meanwhile I'm sitting there doing a slow burn because I've been sitting here forever, and I'm still not getting served. Okay, so we don't want to use a stack for servicing people in a line. We use a queue. So we're adding always objects to the end of the queue. So now Camille comes in. She comes in at the end of the queue. And when the next cash register is free, they take me from the front of the queue. So a queue has two fundamental operations. Now, I understand there's going to be more, but in general, there's two fundamental operations, which is add to the back. I so wish I could figure out how to turn off these notifications while I lecture, but and then we remove from the front. Those are the two basic operations with a queue. Okay? So, we are going to show you how to do it using a linked data structure. By the way, you've already been told a certain way that we probably would like you, a certain data structure that we probably would like you to actually use for this queue. Do any of you remember what it was? Sarah? It was not a list. From the STL library. Oh, I guess list is from the STL. DQ. So this was from several lectures ago, but we told you that a DQ was efficient at removing from either end of a vector. So in fact, if you're going to try to use a queue professionally, please use a DQ. However, we want to show you kind of a gentle introduction, an incremental introduction to how we do linked data structures. And so a nice gentle introduction is to start with stacks, which are simplest, go to queues, which are a little more complicated, and finish with lists, which are the most complicated. So we're actually showing you a linked list implementation for a queue. So how do we do that? Okay, so what we're going to do is we're actually going to now keep three pieces of information. We're going to keep a pointer to the first object on the queue. That is going to be if I remove a object, that will be the object I remove next because it's the front of the queue. Last points to the last object in the queue. If I add a new object to the queue, I will add it after this object. So for example, so the push is adding new objects. So if I said queue push BVZ, I'm going to add BVZ to the end. So last always points to the last node in the queue. And then we also keep track of the size so that we can, if someone queries us, for example, about whether it's empty or what the size is, we can very quickly answer the question. So we're keeping three pieces of information. So when we insert, so there's two operations. We're going to, the push is our add method, and pop is going to be our remove method. Okay? So I am going to start by considering add. Okay, so let's say that, in fact, we say q.push BVZ. Okay, I want to make sure that I use Dr. Planck's pointers. Okay, he's using new node, so I will use new node. Okay, so what he first does is he creates a new node and creates a pointer to it. So that uses the new operation. So he is going to create a new node with BVZ, and he's going to set the forward pointer to null. Okay. Now, what am I going to have to do to update my pointers in this situation? What has to change? There's a couple things that I need to do to get this into the list. Okay, so I have to make last. Again, don't write this down yet. I need to make last. Don't write this down, please. Point to BVZ. What's the other thing I need to do?
Increment size.
Just a second. Okay, I need to increment size. So just like I'm going to try to, so last. Size is 4. There's something missing here. What's the other thing that's missing? Very good. I have to make this thing that points to null now needs to point to BVZ. So I need to make the old last, I'll call it old last, point to new node. Now there's a reason I told you please don't write this down yet. Okay, what happens, do you think, if I execute 1 before 3? Okay, I just did that. I made last point to new node. Yes.
You have no way to get to 6 without iterating all the way through.
Very good. Excellent. I have no way now to get to 6 except by going through first and then iterating all the way through the list, and that's inefficient. Okay? I had a much better way of doing it if I had first, instead of making last point to BVZ, if I had taken advantage of the fact that I had a direct pointer to the last item in the list, I could have easily performed step 3. Okay, so if I had simply first said, if my first step was to say last, and what does Dr. Planck call this? He calls this pointer pointer. Very good. So if he says last pointer equals new node. Very simple. And now step 2 is I just say last equals new node. And then I can increment the size. So the order of operations is kind of important. It really should be this probably should be 1, this should probably be 2, and this should probably be 3. Correct? Does that make sense? Any questions? Okay. Now, there's a special case here. And the special case is, can I erase this? Okay. Special case, what happens if the queue is empty? Okay. The very first time I add something to the queue, it's empty like that. Okay, so let's look at our instructions again. We have last pointer equals new node, and we have last equals new node. So right now with it empty, this is what it looks like. Can someone tell me what evilness or what catastrophe is about to befall me when I execute this piece of code?
Last is pointing to null.
Yeah, last is pointing to null, so I'm going to get a seg fault. I'm trying to do an access through a null pointer. Okay, anytime you try to do an access through a null pointer, you get a seg fault. Last doesn't point to anything. So when you say last pointer, the computer throws up its hands. It says, you're not pointing to anything. And it says, okay, seg fault, dump core. So there's a special case here with the first node, with the first, if the queue is empty to begin with. So we actually have to distinguish between the case where the queue is empty and the case where the queue has some objects in it. If the queue is empty, what do you think just looking at this, oh gosh, getting stuff messed up. I have come on. So I created new node. Okay, so I have a pointer to new node. I set new node equal to a new node. Okay, so the queue is empty. What are the steps I need to perform now? Sarah.
So assuming that we already know it's empty.
We know it's empty. Guaranteed now.
Wouldn't you set the first and last to new node?
Excellent. Set first equal new node. Set last equal new node. And set size to 1. Right? So we have two cases. The queue is empty or the queue is not empty. And it's pretty easy to distinguish between the two cases. We just look at the size variable. If size is equal to 0, then we do the empty case. If size is greater than 0, we do the non-empty case. Okay, so here we go with push, and Dr. Planck has done it a little bit differently. So new node, he creates a new node. Then he initializes the value field to be the string. He makes the pointer be null because this is what we do with new node. Then, at the end, he increments size because no matter what, the size gets incremented by 1. If size was 0, it becomes 1. And no matter what, last is going to get set to new node. That's the same between the two cases. So the only difference is whether we have an empty queue or a non-empty queue. So I'll be honest, I probably would have chosen to say if size equals 0 here. Okay, I think that makes it more clear that we're dealing with an empty queue in that case. His choice, though, is equally good. If last is null, it also means that the queue is empty. Okay? The only way last could be null is if the queue is empty. So either of these two conditions work. Okay? So if the queue is empty, you already saw we set first equal new node, else we set the last pointer equal to new node. Okay? So this is doing exactly what the set of operations I showed you. It's just that we don't have to duplicate operations. We don't have to say if last equal null, then set last to be new node, first equals new node, size equal 1, else set last pointer equals new node, last equals new node, size plus plus. This is what I showed you. But in reality, size equals 0, 1 can be written as size plus plus. This operation, I'll mark it in blue, and this operation are the same. This operation and this operation are the same, and so Dr. Planck pulled those two operations out. Okay, this is the blue operation. This is the red operation. He simply pulled those two common operations out, and this if statement right here determines whether this statement here is executed or this statement here is executed. Okay? So we will pick this up actually in lab tomorrow, and I will see you all on Thursday.